Okay, thanks again, Gordy. So Gordon was a research fish ecologist at the Pacific Northwest Research Station in Corvallis for 35 years and retired in June of 2018. His expertise is in the freshwater ecology of anadromous salmon and trout, conservation biology of those fish, and aquatic aspects of landscape ecology. He has studied the ecology of anadromous salmon and trout in the Pacific Northwest, Northern California, Idaho, and Alaska, and fish ecology in New Zealand and New York. He's published over 100 papers on the freshwater ecology of Pacific salmon and trout, effects of land management activities on the freshwater habitats of these fish, conservation plans, and dynamics of aquatic ecosystems in the Pacific Northwest. He's also led committees that developed and evaluated options for managing federal lands in the Pacific Northwest and Alaska. And his current work focuses on potential effects of climate change on Pacific salmon in Alaska and the Pacific Northwest. And I think one of the things that's really exciting about tonight's presentation is your willingness, Gordy, to really adapt and bring out some research that's come out over the past several years, and as it relates to restoration in the Hood River Watershed and other places, with a sort of with an eye towards the noteworthy disturbance that we have in this watershed. So we really appreciate that you've tailored a talk that relates to the Hood River Watershed and other places, and we can all learn more about the species and the environment we've got here. So thanks again, Gordy.
Okay, well, thank you guys for the invitation. These are always fun things to do, and I want to look at it as an exchange. I mean, I'm going to toss some ideas out there, and that's what a lot of these are, is ideas, and see how they resonate with the group. This is quite funny seeing Elizabeth in here. Elizabeth was in an undergraduate in a class I TA'd when I was a PhD student at Oregon State in like 1982 or 83. So we go back a long way here. Okay, so just to move forward, this is a bit of a modification of a talk that I gave for a conglomeration of watershed groups on fire. And Cindy asked me if we could talk about it in more general terms. The idea of just, challenges that we face moving forward in an uncertain future. And so that's what I'm going to do here tonight. We've got, not to make it a depressing talk, but we got a lot of challenges facing us, climate change, population growth, the number of species that are on the endangered species list and growing. And the challenge is, how are we going to meet these issues and still retain these attributes of an ecosystem and the species that we want? Well, I would say, we look at this quote from Einstein, and I think this is the perfect time for us to start asking ourselves some pretty basic questions and fundamental questions about how we think about aquatic ecosystems and what we expect in terms of the behavior and performance and the organisms that are associated with. So this is really going to be the theme of tonight, is to just lay out, talk about some very basic assumptions that we make that we seldom really question or examine ourselves, and see if maybe we need to have a different perspective as we move forward. Okay, and just as an example, I mean, you can think about riparian zones. Now, it's probably hard for a lot of people to imagine that in the 1950s and 60s and even into the 70s, that center picture was exactly how we treated riparian areas, both on the private and the public lands. Basically, there were no riparian areas. Oregon was one of the first states in the union to have riparian rules. And generally, what you see here in the left side is where we were moving, particularly on the federal lands, prior to the Northwest Forest Plan, which was back in the early 90s. And we defined the riparian areas as along the fish-bearing stream, the fish-bearing portion of the network. After the Northwest Forest Plan, it became much more broadly, the definition expanded and was much broader. So we've done these things, and I did a whole set of other examples you could have, but we've done this thinking and challenged ourselves about assumptions that we made in the past. And I think it's important that we continue to do this as we move forward. Okay, and what I want to really do is look at this concept of resilience, because we think about oftentimes when we undertake restoration efforts, conservation efforts, one of the prime objectives is to make the system resilient. And yet we seldom define what that means. And I think here's an opportunity for us to examine that. Okay, here's the definition as it's been put forth in the scientific literature about the capacity of a system to absorb disturbances and reorganize itself. So it essentially retains the function, structure, and identity that it had before. Okay. Now, if you dig into literature a little deeper, what you see is there are two types of resilience. And this is the classic paper by Ernest Hollings, where the concept of resilience was really, for ecosystems, resilience was really developed. And he identified two types: the engineering definition of resilience. Basically, the system is stable. It's disturbed and it quickly moved back to its the state it was in prior to the disturbance. Okay, and the characteristics of this system is stable. Like I said, it's quick to return to the equilibrium point. It's very predictable in terms of what it should do, and there's a real focus on maintaining attributes. So what this is really talking about is, I think, is how the common perception of aquatic ecosystems and how we perceive them. And one would say, well, what's the basis for that? If you've taken a general fish ecology or aquatic ecology class, you see the basic foundation of that is the river continuum concept. This was developed back in the 1980s by a number of preeminent scientists based on research, primarily in the Northwest. And what you see here is there are predictable features and characteristics of the stream network as you move down through it. So if you start in the headwaters, you've got a production to respiration ratio. You got various producers. You got woody debris characteristics. You move into the middle portion of the network. You start to pick up fish. Again, you have a very defined set of characteristics in there that are unique to that particular segment of the network. And then finally, you get into the lower portions of the network, and you have another set of characteristics. And so this has become the basis for how we view aquatic ecosystems. There's a set of attributes assigned to the different portions of the network. Now there's a concept of change as you move down through the network, but it doesn't talk about change in another sense, and we'll talk about that here in a second. Another conceptual foundation for our view of aquatic ecosystems that fits this engineering definition of resilience is the Rajkin Classification. Dave Rajkin has gone out and, based on his experience, has identified a number of different channel types, and he's articulated the attributes of those channel types, and we go out and we find the channel type, and then we compare the existing conditions to what the conditions that the classification system should be present. And so it varies among stream types, but again, there's no variation in another important manner, and we'll talk about that here in a second. Okay, and then think about it. When we talk about streams, we have these attributes, and generally those attributes are associated with old growth streams that flow through old growth forest, the number of pieces of wood, number of pools, so on and so forth. So we've got a very limited, in a sense, we've got a very limited set of definitions or set of attributes for the aquatic ecosystem that we expect that system to reflect all the time, okay? And, you know, this is something we don't often think about, but and it's something we have to think about because and I'll talk about this later about thinking big. You know, when we think about what do we expect across the aquatic landscape, I would argue that our perception is that everything should have the given set of attributes in it at every point in time, okay? And some people will say no. Now there's some variation. I will, you know, there's going to be some variation depending on locality. Obviously, you know, what you see in the Hood River drainage is not going to be exactly what we see in the Coast Range or what you would see in Alaska. But the idea is there's a very limited range of attributes that you expect, or the value of those attributes is limited. And we expect that everything should be good everywhere. And some people will say, no, I would challenge it, say, well, you know, where do we think differently than this? And this is going to be really important, I think, to challenge this, particularly this stable, static view of systems, because the future is not going to be stable or static. It's going to be much more, I mean, uncertain, it's going to be much more dynamic. And so we have to ask ourselves, is this the perspective we want to move forward with? The other definition of resilience is ecological resilience, okay? So this is the system can reorganize from one domain to another. So in other words, it has attributes across the range of conditions, not just in one domain, okay? It can move, okay? And it had variability. The feature changed through time. And time is a key word here. How do we think about time in terms of aquatic ecosystems? If you go back and think about the stream continuum, the river continuum concept, or the Rajkin channel typing, there's no concept of time built into those foundations. And what happens when we have no concept of time? If we have no concept of time, we have no concept of, we don't consider change, okay? And we'll talk about why that's important. And then in this view, this ecological view of resilience, ecological processes are really key, and we'll talk about that here, you know, as we move forward. So we, you know, look to our terrestrial counterparts and how they view the world. They have a concept of succession, okay? And built into this is a disturbance, and then following the disturbance, there's going to be a change in both the biological and the physical attributes of the environment or the landscape through time, okay? You notice there's a concept of time built in here, and at each point in time, there's going to be, you know, you would expect some attribute to be present, but they're constantly changing. And I would argue this is a fundamental difference between our terrestrial counterparts and ourselves that we seldom recognize. And I think, you know, I've been involved in the debate between fisheries, the fish biologists and the foresters for 40 plus years. And we're still arguing, yes, it is, and no, it isn't. And I would say that the fundamental reason for our differences come down to these worldviews that we seldom explore. And so when we talk about disturbances, be it floods, be it fires, our terrestrial counterparts often have a very different response to them and different set of expectations than we do. Now, primarily what happened when you think about these disturbances, it's going to be the legacy of the disturbance really sets the stage. That's what's left over. The aftermath of the disturbance is really what allows that system to recover and move forward with. And so what we should really be thinking about, I would contend, with a lot of our restoration projects is not necessarily, I mean, stopping some disturbances. Now, I'm not going to argue that every disturbance is going to be a plus, but many disturbances that we see today, we can take advantage of if we think about them in terms of what's the legacy of the disturbance and how's the system going to move forward with that. So I would suggest that from our terrestrial counterpart, this is how they view the landscape. it's a shifting mosaic of conditions. And what you see here, this is Western Oregon, and a modeled simulation of what it looked like, pre-European man. And what you see is that nothing is stable. That these patches, the darker the green, the older the tree. So the real dark green is old growth. The lighter are recently are young stands. And what you have here is a mosaic that is constantly shifting around that landscape. It's not stable, and everything isn't necessarily in the same state all the time or at any point in time. And this may be a little hard to see just because of the colors, but what this illustrates is its variation associated with scales. So if you're down at, this is a forest stand, the reserved scale down there, you have a tremendous amount of variation through time. And you would say, how did this happen? Well, you can imagine if you could suspend yourself in a balloon above a patch of ground for 3,000 years and you watched it. Now, this is the Coast Range. It may not, it wouldn't be the same for the east side of Hood, but you would see, I think you'd see the same phenomena. You would see periods of time where you had tremendous amounts of old growth and lush forest, and then a period of time following a fire where there was a completely different setting. And this would vary over time. But then you pull yourself up to a higher level in that balloon, and you look at a larger landscape, and what you're going to see is there's going to be some patches, because the disturbances aren't necessarily so large that they affect everything at one time. And then if you pull yourself even higher in that balloon, and you were to watch all of Eastern Oregon, for example, or all of Western Oregon, you would see that it's relatively stable, that pattern. Now, the location of the various pieces are not stable, but the amounts that you see in that landscape are going to be relatively stable through time. And we're starting to see this in the fisheries world. This is some work from Daniel Schindler and his colleagues at Bristol Bay, where they've been monitoring salmon populations for going on 60 or 70 years. And what you see here is you look at individual streams here on the left, and what do you see? You see a tremendous amount of variation in time in these streams. Now remember, these are streams that essentially have no human impact in them, okay? These are, if you want to find natural streams, this is the place to go. And so you see there's a tremendous amount of variation. Then you scale up and you go to larger river system, there's variation, but not nearly as much. And well, I'm not sure what happened here, but if I showed you Bristol Bay as a whole, it'd be very similar to what you see, we saw in the Coast Range there for that province. It'd be very stable at that point. And this is just another example of this year-to-year variability. This is some work that was just done by a student of Daniel's, Sean Brennan. And what he looked at, well, what he did, he was trying to determine the production from different parts of the Nuchagak River, which is part of Bristol Bay. And I should just say the Nuchagak River, that upper right-hand part, or that whole right-hand portion of the network, was where Pebble Mine was going to be. So this was a place that the Pebble Mine would have completely compromised. But what you see here is the upper panel represents Chinook salmon and Chinook salmon production in three different time periods: 2011, 2014, and 2015. And what you see in that, even in that relatively short time, look how things have moved around this landscape. So the darker the red, the higher the level of production. And the same thing for Chinook. In fact, it's even for sockeye. I think it's even more dramatic for sockeye in that 2-year period. How things have shifted around. So again, stability is not is not part of these natural landscapes. The variability is really high. Now I'm just going to diverge for a second, because when I was talking with Cindy and Alex, she asked me how they were able to discern this information. Well, what they used was otolith microchemistry. in fish that were captured in the commercial fishery, and then from the spawning grounds. And the otolith is a bony structure that's in the head. We think it's analogous to our ear bone. But the really interesting thing about the otolith, it lays down a ring every day. So if you could count the number of rings in there, you could tell exactly how old that fish is, not to the day. And it does this by, and what you're able to do then is look at the chemical composition of different portions of the otolith and understand where, understand about where the fish was in terms of its environment, and then where it was at different points in time. And so this is a Chinook salmon from the mid-Columbia. This is from McMichael and Lance Campbell, who's with the Washington Department of Fisheries, who's really the master at all this work. And what you see then, they're looking at the strontium calcium ratio, and the strontium calcium ratio happened because in saltwater, strontium substitutes for calcium in terms of bones, okay? And so what you see here is that that maternal signal, that was the signal of the yolk of this individual. And you can see it's high, so that's the maternal signal. And then it goes down where it emerges, and it spent time in fresh water. And then you see it start to go up, and it goes to the estuary. You see it begin to rise, and then it goes to the open ocean, and you see a completely different signal. So you can tell a lot about an individual in its life history from this. We've used this technique with other elements to actually track the movement of fish within a watershed. So if you've got a strong chemical signatures from the geology changing, you can actually tell on when and for how long a fish was in a given part of the watershed. The other thing you can do is look at another portion of the life history here is looking at the relationship between rainbows and steelhead. This is work that Chris Zimmerman and I did with Chris. Chris did the work on the Deschutes. And what you see here is just a couple different examples on the Deschutes River. That top one, you see that signal is the strontium calcium ratio is high, and that's because the maternal parent was a steelhead. The yolk had a high strontium calcium ratio, and then it spent time in fresh water, and then it moved and went into the ocean. There's the Babine River steelhead. The maternal parent was, again, a steelhead. It spent time in fresh water, and you see much less time in fresh water than what we saw for the Deschutes. And then it moved into the marine environment. And then what you see in that middle is the Deschutes Rainbow. And you can see how even that is, because the maternal parent, again, the signature of the yolk is much different than from a steelhead. And what's really interesting is the Deschutes, as far as we can tell, is the only river so far that we know about where rainbows don't give rise to steelhead and steelhead don't give rise to rainbow. It's the only one, okay? And here's an example where you got a Babine River rainbow whose maternal parent was a steelhead. You see, you get that high strontium calcium ratio, and then it levels out. And so there's a lot to be, a lot of things can happen. It can be learned from using, looking at the otoliths of fish from the basin. And we can talk more about that later. But I just wanted to just bring you up, make you familiar with the technique that was used here. Okay. And this is, the stability of the river system that's just not in the fish. This is work I'm doing with Daniel Schindler and a grad student of his with wood, counts of wood. Now this is from Elk River down on the south coast of Oregon, where we counted every piece of wood in about 70 kilometers of stream for 16 straight years. And what you see here are those numbers, okay? And again, it's anything but stable. The The numbers are going up and down. In between 96 and 97, there was a major flood. You see that dramatic drop, and then things pick up again. So even the physical attributes of our systems are not stable. They're highly variable and over time. There's a paper that I think if you really want to get into this, it's an older paper. It's from Bob Nyman and a number of students that he worked with about attributes of a healthy watershed, and they talk about the dynamics. And one of the things they do is then present this idea that the headwaters, you have different types of dynamics depending on where you are. Very similar to, you can think about it as the river continuum, but instead of attributes, they're talking about dynamics and variation. And in this upper part of the watershed, these streams periodically experience a major disturbance in the form of a landslide or debris flow. And this is some interesting work by Bob Gressball and Christine May, where they looked at the evolution of these channels over time. So they evacuate, and then over time they refill with sediment and wood, and then they discharge again, and they go through this cycle. In the Coast Range, it's probably on the average about 200 to 250 years. Now you say, well, why is this important? Well, two things. One is that there is, these streams are important sources of wood. In the Coast Range, we've seen that 40 to 60% or more of the wood actually come from these headwater streams, and they come in the form of debris flows, okay? The other thing we know, these headwater streams are important sources of cold and high quality water that are delivered to these to the fish-bearing streams. These are sites of amphibian biodiversity. Just if you want it, these small headwater streams are just rich in amphibians, and they really make use of these areas. The other thing is these headwater streams deliver tremendous amounts of resources in the form of food and nutrients to the fish-bearing streams. In Alaska, some work by Mark Whiffley has shown that 50% or more of the invertebrates in fish-bearing streams are originating in these small headwater non-fish-bearing streams. And so they're an important contributor to the productivity of the fish-bearing portion of the network. Okay, and then we look at the middle portions of this network, and again, you notice that this is even much more variable in time than those lower portions, those upper portions, I should say, because what you have now is the number of streams entering into this middle portion is much higher. So your potential for disturbances is much more frequent. So these, again, are not stable. They're highly variable in time. And this is just an example of what it looks like in the Coast Range, where you go from a system that is primarily sediments to one that's a mixture of sediments and wood, to an old growth system, which we consider to be best. But old growth systems, in many cases, have tremendous amounts of wood, but they lack other attributes, primarily sediments. And so they may not be the best. In fact, in the Coast Range, these streams that were about 140 to 160 years from disturbance were actually the most productive from a fish perspective. Another example of this are these wet meadows systems that we see. And there's a tremendous amount of effort on the east side put into restoring these wet meadows. Well, this is some work from Steve Wanzel, Pete Bisson, and some others on the behavior of these wet meadow systems. And you start there in the upper right system, where we have these climax wet meadows, and the reason we have it is the water table is high. And the reason the water table is high is because the channels are graded, okay? So if we go without disturbance, what happens, that there's going to be transport of the bed material, and you're going to begin to down cut that channel. And as you down cut the channel, you lower the water table. And as you lower the water table, you begin to change the the nature of the vegetation on the floodplain, and you began to lose some of the attributes of that wet meadow system. It looked like what maintained these wet meadow systems were fires. Think about, and the erosion following fires, okay? And think about what we do, one of the first things we do following fires. We try to stop erosion under the guise of protecting things, okay? Now, maybe infrastructure, other things, that's one thing, but we shouldn't be arguing that by stopping erosion, we're protecting our stream system, because we may not be. We actually may be leading to further degradation by preventing erosion. So one of the things we've done is similar to what we've done with wood, where we can identify the attributes of channels that fail and deliver to fish-bearing streams. We've done some work on the east side where we can say, okay, here are the streams that after a fire are likely to have gully erosion that's going to lead to the introduction of sediments into that valley, those valley floor segments of the stream network, and may be actually quite favorable. So I think as part of our restoration effort, we should be thinking about how do we take advantage of these events, such as fires, which we've not done a very good job of previously. When we were talking, Cindy asked me to talk about glacial floods. Okay, I tried to. I feel like I'm really on weak ground here. Okay, but I just some ideas. All right. I spend a lot of time in Alaska, particularly up on the Copper River and the Copper River Delta. And if you want to see a landscape that's been shaped by glaciers, it is the most incredible place in the world, I think. You have these glacial rivers just everywhere. And what's really interesting, the glacial rivers look like chocolate milk. I mean, you can, in the summertime, you couldn't see your hand in front of your face. But if you move laterally across those floodplains and get to the channels that are further and further away from the main channel, turned out that these are really productive areas for fish. Now, in this case, we were looking at Chinook. This is part of in the upper Copper. And what's interesting is their diet. They're feeding on midges, okay, which we often assume you associate midges with poor water quality. And the midges here are there because of the glacial flour. There are tremendous amounts of fine sediments in many of these systems, and we usually dismiss that because they don't have the big three, the Ephemeroptera, Plecoptera, and Trichoptera. But it turns out that these areas, these backwaters that have relatively clear water and this fine glacial sediment, are really productive for midges, and the fish are really taking advantage of those. So they may be really important areas. Now, the other thing is, many of these channels that we go to in, say, June, July, and even August, we look at them, they're highly turbid, and we say, well, nothing goes, biologically, they're just, essentially a desert. But it turns out that once those glaciers start to the temperature drop and they start to freeze up, the water clears very quickly. And what we see in Cordova and in other parts of the Copper is the fish make extensive use of these areas for spawning. That they're in just really important areas. And this is showing some sockeye. We were doing some freeze core work here, but you can see this stream. If I had been to this stream a month before, you wouldn't have seen anything under the water. Okay, this is like late August, starting to get cold into September, and the fish are there spawning in them. And there's fish, and sometimes in some of these systems, fish are spawning in December and January. And if you're not out there to see it, you don't see it. So I really think that we should be really, don't dismiss these glacial streams and these areas that look like they've been disturbed just automatically because you see something during the summertime. These can be really, really productive places on the landscape. Okay, so what have we learned? Okay, I think when we look at this, we've learned that change is more important than stability. Understanding processes and interactions is more important than a description of conditions. And when we say this, we'll talk about this, it's like identifying where these processes play out on the landscape is really critical. And then extreme conditions can be in many cases be more important than average conditions. And here's an example of the processes where we look at sources of wood. And what you see here is the black represents where the wood is coming from the immediately adjacent riparian zone, as opposed to coming in via landslides, okay? Now, the other important thing about landslide origin wood is having wood in your landslides completely changes the behavior of the landslide. It slows it down, it moves down the slope much more slowly. And when it hits the valley bottom, it tends to set up and it's not moving downstream. There's been some really interesting work by Gordon Grant and Stephen Lancaster on this in the Coast Range, and it shows that having that large wood entrained in the landslide makes the system respond in a very different way, not just to the landslide, but think about, we talk about the legacy. Now we got a legacy, we got the building blocks for good fish habitat here. We've got the large wood and we've got the sediment. And this is how they're introduced. They're introduced in each catastrophic event, and then the system works with them through time. This is just an example, a landscape level analysis where you can identify where in the landscape these things are going to occur. I think this type of analysis may be available for the Hood River. The Forest Service, this is work we did as a pilot effort in Western Oregon, where we looked at downscaled climate change projections for temperature and flows. And as part of that, we did this landslide work. I think, and I didn't have time to check it out after I talked with Cindy and Alex and I talked last week, but I think this level of analysis is available for you guys from the Forest Service for Hood River. And then you can, with this, you can begin to become much more strategic and effective in directing your restoration efforts. This is just showing with landslide, with road removals and culvert placements. And the same thing with water temperature. What we see here is that, we think about, climate change and water temperatures, and it turns out that everything isn't going to respond uniformly with regard to water temperature. There's going to be a lot of inherent variability. And this illustrates that very nicely. This is, again, this is the Applegate. This is down in Southern Oregon. But what you see here is there's tremendous amounts of variability. We have it now, but it's even going to be more apparent in the future. Some areas are going to just be very susceptible to warming, and others are not. And we should be able to use this information to help us be more strategic in where we go to help address climate change. So for example, one of the things we can do is look at where riparian vegetation makes a difference with regards to water temperature. So you can think of, we often think, well, if we have temperature issues, it's due to riparian vegetation. In some cases, yes. In other cases, it may not be. Okay, and the improving riparian conditions in some cases may not really lead to address the water temperature issues. And this is just showing these red areas on this map are areas where the riparian vegetation would make a difference with water temperature. And again, you see it's not everywhere. Now you say, why is that different? Topographic shading, stream orientation are the two other big factors, and they oftentimes override riparian bed. So if you're thinking about riparian bed from a temperature perspective, again, being strategic, it may lead to improve our chances for success. This is talking about pretty much the same thing, just at a larger scale. One of the things also that we're looking at, I'm sorry, this is looking for off-channel areas. Because one of the things we know is almost certain that we're going to be, see higher flows during our winter, just because more precipitation, and also because we're going to transition from snow to rain. And so the idea here is we need to reconnect the floodplains in the channel. Think about what happens as we get more and more water in that channel. If we allow that water to remain in it, it has tremendous amount of energy and it scours and wreaks havoc on the channel bottom. That's when we have issues with scouring of reds and mortality of developing eggs and embryos. If we can allow that water to dissipate laterally across the floodplain, we can offset the effect of higher flows in our channels. And so what we should be looking for are opportunities to do this, where we can reconnect, allow the floodplain to be reconnected to the channel. So when flows come out, it comes up on the floodplain. The other thing that happens there is that if we have these off-channel habitats, oftentimes they're really important places for fish to grow and rear during this winter period. Now, we often think that, we're not going to see much growth or production during the winter, but in many of these side channel, these off-channel habitats, conditions are conducive to actually having fish grow. And these are going to be important. The other part of this is we know oftentimes with our smolts, they'll make a transition in the fall to the lower portions of the network, staging before they make that final push in the spring. And they use these off-channel habitats and small streams associated with are really important. So being strategic and where we can reconnect these, find these and reconnect them is really important. Okay, and then starting to close here, we've talked about this idea of system being dynamic in space and time. Well, how did fish adapt to this? What did the fish do that allowed them to persist in such an environment? Well, if you begin to look at the life history attributes of the native fish, particularly Pacific salmon and other salmonids, you'll see that they're highly adapted to these very dynamic landscapes. They've got genetic and life history flexibility, which allows them to sort of hedge their bets against this uncertainty. There's straying of adults. We think about straying in terms of, when we talk about it, generally perceived to be a negative attribute, and it's usually associated with hatchery fish straying into wild populations. But it turned out that there's usually a pretty substantial segment, 15% or more of a population may actually stray to new watersheds that may not come back to the same place. And think about this, if you're in an environment that is uncertain, one way you can persist as a population is to continually throw new seeds out there and explore and find new areas. The other thing is we know that these fish have a very, very high fecundity. This is the sort of the number of eggs per unit of body mass, a unit of length. It turned out that Pacific salmon are some of the highest fecundity rates of any of the fish in the world. So again, so what does this remind you of? You got something that has a really high fecundity. It has a high potential for dispersal. I like to call the fish we're trying to conserve and restore the dandelions of the fish world. They've got this incredibly high capacity to respond to this dynamic environment. And we should be taking advantage of this. And finally, we talk about where we've changed our perspective on things. When I first went to school, there was papers by Don Chapman where he was looking at juvenile coho salmon, and he noticed there was this tremendous movements periodically. And he associated that movement or attributed that movement to individuals that were least fit, or they were less fit than the resident ones, that they were ones that couldn't obtain a territory, and so they were leaving, and they essentially were lost. He labeled them nomads. Well, it turned out that those were just other life history forms, and those were important, again, just like the straying of adults, these were important for maintaining this long-term productivity. General patterns are more important than details. Think about how we just want to drill in and get 3 pieces of wood or so on. we should be looking more for patterns than the details. And, you know, we know uncertainty is going to be uncertain, and it's probably going to be even greater in the future than we have. And so we should be acknowledging this and thinking about how we build in our ability to deal with it. And then finally, the focus should be on diversity. You know, think about when we do restoration, what our goal is to get, quote, more fish, okay? I would contend that really what we should be thinking about is how do we increase the diversity of those populations. This is just an example. This is some work we did at on Elk River. But you look at, this is from Paul Reimers, where he identified for fall Chinook salmon 5 life history types. Everything, you know, like these numbers that you see here correspond to the numbers here on the chart. Things that spent just essentially were pink salmon. They spent very little time in the tributaries, the main stem, they went to the estuary and then they were off, okay? To fish that spent a whole year. Now, what's our perception of fall Chinook? They usually spend, you know, 3 to 6, 9 months in fresh water before they move on. You see there's a whole lot of variation here. And what was interesting is what Paul saw was in any return of adults, it was dominated by one of these life history types, okay? Now, first of all, the reason these life history types could be expressed was because the landscape allowed it. In other words, they had an intact estuary, they had habitats all along the main stem and the tributaries that these fish could use. So there was a string of beads, if you will, that allowed this expression to happen. But what was really neat, one of these life history types would dominate the return, and then the offspring from those would express all of these life history types. So even though the life history study obviously wasn't just a genetic component to it, there was something else. Even though, you know, number 3 might be the dominant return in any one year, the following year, you would see all 5 of these life history types expressed. Okay, and we're seeing this as examples in the Elwha. George Paston and company are doing some really interesting study in a relatively short time, seeing these life history type re-expressed. This is some interesting work that Dan Bottom and Kim Jones have done in the Salmon River over on the coast near Lincoln City. And they took out tidal dikes. And just an illustration of how quickly fish can respond, you see here on the left, the life history types that were prior to the removal of the dikes. And look at after the dikes, it was completely, and this is in a relatively short time. So these fish that we're trying to restore and conserve have a tremendous capacity to respond to changes in our landscape. And that's what we should be doing, is giving them a landscape in which they can respond. And this is going to be the key to moving forward, is diversity. And having a landscape that allows this life history diversity to be expressed. And, you know, the perfect example is going to be what Rainbows and Steelhead. You know, oftentimes we're trying to restore our steelhead population and we're completely ignoring the resident forms. You know, Mike Bluin done some classic work with on steelhead and hatchery effects there in Hood River. But one of the more interesting things, I think, from Mike's work is how he found that about 40% of the steelhead actually had rainbow parentage. And so, you know, one of the things we need to be thinking about is maybe being more encompassing of these other life history types to help us with this restoration, and not just focus on just trying to get steelhead. In order to get steelhead, we need to protect the rainbows. Okay, I'm going to stop right there, and but let me just make one more point. The other important point here is that we're not going to be able to save everything. You know, some of the fish we're trying to conserve and restore may not have the attributes that the inherent attributes that they need to be successful moving forward. And we should be thinking about that and and acknowledge it and just understand that. And this is some work we did as part of the science review for the Northwest Forest Plan just before I retired. And one of the things that we identify what we think are these idea of winners and losers. I would really encourage you to look at this and see what you think about this concept about who might win and who might lose. Okay, so with that, I think I think the bottom line here is we got to go big in terms of our thinking, the area we work in, how we think about things, think about diversity, life history diversity, variation, or we should just go home. So with that, I'll open it up to comments and questions.
Folks, feel free to unmute yourselves.
Yes, I have a
There's
question.
a lot of
So you emphasize the importance of the major extreme changes, but I think what's also implied in here is that in between those major or extreme events, there is a extended period of gradual change. Could you discuss that, please?
Yeah, I mean when we talk about the extremes, I mean that we need to see these extremes. These extremes are going to occur on the landscape, but they're going to be leading into, as you just touched on, they will lead into the gradually, or in some time, gradually set the stage for becoming more productive. And the idea would be when we see something like a large storm event, a flood event, a fire, that I often look at that as it's resetting the system. And now what do we have? What does that system have to move forward with? The legacy, if you will. And that what we're going to see then is that gradual change. Do we have the elements there to allow that gradual change to be beneficial? And then secondly would be recognize that there's going to be, that all these things aren't going to happen at the same time. So you're going to have a lot of, you should look at that landscape as having a lot of inherent variation and not being necessarily uniform.
If I may follow up on that, I think one of the expected effects and observed events of climate change is that what used to be infrequent extreme events are becoming more and more frequent. I would expect that has implications for the winner species in your winner-loser slide, in that the winner species would be those species that can tolerate more frequent extreme events.
Or yes, I mean, in that could be one way to do it. Or do you have a landscape in which they could, that can absorb those events, and you have a legacy from those events that allows then productive conditions to evolve.
I think one of the applications of what you've been talking about, Gordy, that I've been working with over the past couple of weeks during the action plan writing was thinking about the Hood River Watershed. And some of the tributaries are heavily influenced by glaciers. So Elliott Creek, to a lesser extent Coe Creek, Clark and Newton Forks, heavily impacted sort of by mountain activity and glacial activity. In contrast to the Upper West Fork that has some spring-fed systems, Neal Creek that doesn't have glacial influence. And just thinking about the landscape diversity in the Hood River Watershed and making sure that we're not only focusing on just the glacier streams or just the, sort of the non-glacial streams. That's one of the take-homes that I've gotten from the papers you've sent and the work that you've talked about.
Yeah, and no, I think that's a really good example, Cindy. And I think it's clear is just then sort of understanding the behavior of those systems and how they're going to behave. You know, you expect them to behave in space and time, and the attributes they have. One of the interesting things that, you know, we hear about glacial streams and quote, they're too cold, right? I sent Cindy some work that we just finished up and had published from a grad student, Emily Campbell, up in Cordova. And we looked at Coho this is on the Copper River Delta. And we looked at a stream that was, quote, ideal, okay? I mean, the water temperatures were in the 10 to 12 degree range during the summer, which if you look at the literature, says that should be ideal for growth for Coho. And we compared that to a stream that was 4 degrees almost every day of the year with the groundwater system. And we did this with spawning and emergence and then growth. And what was interesting, the first thing was we noticed that in the fall, the fish in the, quote, ideal stream, now in the wintertime, it went to 0. The system essentially freezes. The fish spawned, the coho spawned 8 weeks earlier in that system than it did in the groundwater system, which was 4 degrees. And yet the eggs emerged, the juveniles emerged at the same time. And you say, well, how does that happen? Well, you think about it, you know, if you think about the development process, it's all premised on the accumulation of heat. And so you have to accumulate heat in order to develop. So when you're in the surface water system, you spawn in the fall, the water might be 7 or 8 degrees. You're accumulating a large mass of heat. But then winter sets in and it hits 0 or close to 0 for a long time, and you don't get anything. And then spring comes and you get a lot of heat. Think about what happens in the groundwater system when the fish spawned 8 weeks later, okay? They were getting 4 degrees of heat unit every day. So you know, this is analogous to the tortoise and the hare. In the ideal system, the tortoise got in there, he got a lot of heat, and then he got nothing for a long time. Then he decided he needed to catch up. The turtle, you know, the tortoise just took that 4 degrees every day, and it was very interesting. They emerged at the same time. What was even more surprising was at the end of October, the fish were the same size. The fish in the ideal condition, that 10 to 12, 10 to 13 degree stream were the same size as the ones in the 4 degree stream. So there's a lot of local adaptation that's going on. And so I think we need to be careful when we label things too cold or, you know, not ideal, that we dismiss them. And it may be that those are really important. They've got really unique features of them, and the populations in them may be highly adapted and really really valuable to be maintained in the landscape.
Hey, Gordy, this is Lucius Caldwell. Well, first of all, I just wanted to say thank you. This was a super interesting talk. I really appreciate you taking time to chat with us all. And I have a follow-up question on Cindy's question/comment about sort of the applications of this. You know, you spoke a lot about disturbance, resilience, and diversity, and I'm thinking about like how do we take this information and kind of act on it, right? So what I was curious about was, you know, particularly in light of this, the importance in terms of like geomorphology and streams and stream ecology of very large wood. What do you think about, what's your thought about forest management alternatives that aim to mimic that level of the scale and intensity of the disturbance? Like, you know, people are throwing out these seemingly crazy ideas of like clear cutting an entire catchment on a hundreds of year rotation instead of like a 30-year rotation. You talked about this like 140 to 160 year optimum for production, or Bob Nyman's 250 to 300 year interval optimum for large wood. Like, yeah. What would your take on that be? Do you think that's a valid application of some of these ideas, or is that way off base?
No, I actually think, you know, in some ways that may be a more prudent way to proceed. You know, how I view timber harvest, I view timber harvest as the new disturbance element on the landscape. In other words, it's replaced fire in many cases, okay? But think about what we try to do. We try to maintain stability with timber harvest. You know, we leave a riparian area along a buffer along our stream to maintain stability. And maybe what we should be doing is setting that system up so that it's going to fail when it fails, and it will fail at some point in time. It can move in a positive direction, and then, you know, if you have these longer rotation, it's got more time to work with that legacy. So that may be, you know, from a conservation perspective and from a restoration perspective, I think that that's certainly something that is worthy of consideration.
Well, if you clear cut everything, then there wouldn't be any wood to transport down a stream. Like if you,
Yeah,
you know,
I don't, I want to be clear. I'm not talking about just going in there and wiping it out. That's, I mean, you'd have to think, you'd have to be, you know, be very strategic in what you do. In other words, for example, where you leave big buffers, okay? You would leave big buffers in key parts of that landscape, both along the stream and the upslope areas, with the expectation that there would be some failure at some point in the future. I mean, I think the key difference between what we have with forestry, with timber operation, you know, when you're on a 35-year or 40-year rotation, you're coming in and turning that system over very quickly, and you're removing all the legacy, okay? That's not what we're talking about here. I think we're talking about a big area and trying to emulate a fire, which would, you know, you'd be much more patchy in your activities. You leave a very different legacy, but I think it's worth consideration. And again, I'm not talking about total clear cuts. I mean, you got to think about forestry in a very different way, okay? But I think it is worth thinking about it from a land management perspective. It may, and from a conservation and restoration perspective, it may be, I think, one of the better avenues to pursue.
Interesting. Thanks, Gordy. Appreciate it.
Yeah.
Hey, Gordy, this is Elizabeth, and
Yeah.
These are some pretty big ideas. And what are the opportunities to set up some experiments to test? Or, I mean, you did illustrate some research starting to you know, confirm some of what you're saying, but is there an opportunity, for example, in the Clackamas where we had the huge fires? Are there some opportunities presented by the fires to do some experimental learning?
Oh, I think the fires have presented an enormous opportunity for us to learn. You know, you know, most of us are, you know, most people have probably said, oh, the fires are a disaster. I would be willing, you know, Fish Creek, I think, Elizabeth, would be a great place. Fish Creek just got toasted, as far as I know.
I was hoping you might mention Fish Creek. Thank you.
Yeah.
All the work, how many millions went in?
No, but I would be willing to bet that Fish Creek, if we just leave it alone, let it go on its merry way, Fish Creek will be an incredibly productive stream not too far down the road. I think you know, if those components, you still got a lot of big trees in that landscape, you got a lot of sediment that can be moved. I would be willing to bet that things will be quite good in the next 5 to 10 years in Fish Creek for fish. You're muted.
Fish Creek is just over the hill on the Clackamas in the Estacada area.
Well, you know, I mean, I first got on, what really got me excited about this is the first time I went to Yellowstone, I just happened to be there in 1988. And it was, I mean, my God, it looked like World War III had started in that place. I mean, it was just amazing. And it was, you know, I mean, the fires were just incredible. But what was really interesting was how the fish responded. And that place boomed after the, you know, a few years after the fire. And even now you still see the legacies of that. that, you know, the fish population didn't suffer. You know, you had that life history diversity, you had the connectivity in that system, and you had an incredible legacy of that fire. And the combination of those things allowed it to be a positive experience for the fish. You know, and again, part of this is this connectivity. You know, do we have the ability to fish to move, you know, across this landscape and allow these life history expression to happen? So I think some of these things are definitely worth, you know, worth doing, and we've got some places now we should be able to do it. And hopefully we got a, you know, administration that'll allow us to do it.
Could I ask a follow-up question? I can't see if other people have their hands up or anything.
I have one, but I'll wait.
Oh, go ahead, go ahead. I can come back.
You know, we often talk about these forests, really, or, you know, rural, the rivers and creeks that are going through there, but you know, so much of what impacts our rivers and creeks are, you know, going through town. I was looking at, you know, Bear Creek down there going through Ashland and Talent and Medford and, you know, winding through
Right.
all of that landscape. And then the Willamette, you know, going through, you know, just one continuous city after another.
Yeah.
You know, we always look at all the sort of the damage to the riparian areas because of logging, but we don't often talk about, well, what can we do about the damage to the riparian areas and all these urban things and rural developments.
Yeah, I mean, you know, the urban environment is a challenge unto itself, and you know, I think that, you know, there's a limit to these crazy ideas that I'm throwing out here, and certainly, you know, like you don't want to see major floods in urban areas, or we don't want to see fires in urban areas. But I think what we should be able to do is recognize that, okay, it's going to take a much more concerted effort, and maybe some different things, and a much more, I think, sort of a consistent effort, a constant effort to restore those things in urban areas, because you're going to have to be constantly in there helping, you know, that riparian area grow, doing other things that, you know, it may be that you're going to have to introduce sediment periodically that the floods would have done, and recognize that when you constrain the channel, you change the whole dynamics of not just the channel itself, but the ecology of that system. You know, instead of having, and maybe what we do is look for places, and be strategic. Where can we reconnect the floodplain? And it might not be every mile, but there may be some places where we can do it, and we should take advantage of those. And then recognize, you know, put into perspective sort of that our ability to be successful maybe it's going to be somewhat limited. And that's fine. I mean, I think that's just a realistic assessment that we should have, rather than, I mean, one of the things I think with our own worst enemies, when we promise things that we can't deliver, or we promise things that are just so unlikely that we can't do it. I don't think that does anybody any good. We should be able to say, this is what we think we can do realistically. And I think the urban environment is a perfect place for us to be able to do that.
Oh, thank you.
Yeah.
No, I think we're going to have to come up with something, because there's just, as one of your first charts showed, that population growth is expected to be that sort of exponential.
Yeah, yeah. And, you know, in Oregon, it, you know, could be a climate refuge, you know, for people from the Southwest. And that could send that trajectory off onto another whole different one, you know.
Yeah, I just heard the state of Washington is expecting 3 more Seattles in the next 50 years.
Yeah, yeah.
Does anyone else have any questions? Elizabeth, did you want to say something again, follow up?
a little bit of a follow-up, and it's with regard to sometimes we get this sense that lately we're feeling a little bit of a race to, climate change we're experiencing, and are we, we're seeing that it's happening at a rate a little faster than anticipated. And I guess, Gordy, when it comes to experimental design and our sense of urgency for addressing climate change, I mean, the types of experimental designs that you're talking about now, how would you think about prioritizing those to inform us what's the most important thing to do in terms of restoration or conservation in the face of the changing climate?
Well, I think the main thing, Elizabeth, would be just a critical examination of not just the work we've done, but the underpinnings of that work. In other words, what was the foundation for why we did X, or why we did Y, or why did we expect this and expect that? And that, I think, an honest assessment and an objective assessment at that level is really critical. And then what we could, I think, that would then lead into, let's try some new things. Let's do it in an experimental way and try it. And maybe, as part of that, reset our expectations. If we're saying that we're not, we want to increase diversity as much as numbers, then we've got to go about the restoration, the monitoring of the restoration much differently. If we're talking, and we might say, well, we need, it might take 10 years as opposed to 5 years or something. So I think the first thing is this really objective evaluation, and then from that, I think, would flow some new ideas about how to do things, the scale at which we approached it, and how we would do the effort. And in many cases, I think we should be looking for the opportunity to present themselves, like these fires, these floods, I think are really important events that we should be taking advantage of and not looking at in terms of a negative sense, but in terms of how do we make them into being a positive event.
Oh, that we should head out to Elliott Creek after the next debris flow and start sampling, for midges and
Yeah,
things like that.
We were talking when Cindy and Alex and I were talking last Thursday or Friday, whatever it was, what day. One of the things I pointed out is, think about how what we use to make all of these statements about streams. That one's good and that one's not, or fish do this or fish do that. If you look in the literature, we basically study fish from 10 to 2 during the summer, between 10 o'clock in the morning and 2 o'clock in the afternoon. And, so that's 1/6 of the day and 1/4 of the year. That's roughly 4% of that life, of that annual life of the fish that we look at. And yet we make all of these assumptions, and, we have to make some assumptions, but I think it's important to, to question, how accurate do we think those assumptions are? And when we say this is too cold or there's too many fine sediments, did we really think through thoroughly what that meant or why we said it?
Okay, well, I wanted to make just one observation that I got from your talk, and that was, you talked about diversity was so important, and in the Hood River, we are one of the most diverse. We have one of the most diverse array of fishes in the river. and which we've always been proud of and happy of. But then further in there, you had that continuum of the specialized fishes are the most in danger. And I saw a number of the fishes that we have that are, you know, fall in that round, and our winter steelhead, and well, I wouldn't say our fall chinook are doing that great, but at least the winter steelhead are in the more the area that can take care of itself and do better. And you know, the idea that we need to do what we can, well, and that's where I think the plan that Cindy's been working on, or we all have been working on, but Cindy's been writing lately, you know, we really have a big, our 2040 plan is lined out a lot of projects where we can take advantage of doing what's possible. And I just see your talk as, you know, just emphasizing how important that is to do what we can. And to, in a lot of ways, it seems like just get out of the way of the processes that can happen naturally by not impinging on them too much. Now, that might not happen so much in the farming valley, but up in the forests, if we have a little more protection around those tributary streams and whatever, we might be able to take advantage of the natural function of rebuilding. So.
And
Okay.
I just want to just say, you know, just because that, you know, we say it's more, you know, more susceptible, or, you know, winners and losers, that doesn't mean they're going to lose. It means that we probably got to do more work, you know, in terms of our landscape. It would take, you know, we need to think harder about those guys and how we're going to do it, and be really strategic in what we do. But again, I really think diversity and an emphasis on life history diversity has really got to be part of any restoration and conservation program to move forward, because that's going to be the key to meeting any of these challenges, be it population growth, climate change, whatever. That maintaining that diversity is what's allowed these fish to persist for millions and millions for thousands and thousands of years. And we, you know, I think we lose sight of that. And in the conservation and restoration programs many times. And so I think that needs to really rise to the front and become a real focus of what we do.
Okay, with that, I'm gonna say thank you to Gordon Reeves, and everyone go out of mute, and we're gonna give him a round of applause as we usually do. So unmute yourselves or show your yellow hands.
Thank you.
Great, thank you.
Thank you.